Besides angles being inscribed in a circle, you could also have inscribed polygons. And a polygon's inscribed in a circle if you have all of the vertices of the polygon that lie on the circle. So just starting off with the polygon with the least number of sides, a triangle. A triangle could be inscribed in a polygon. If I have all three of the vertices, call them A, B, and C of the triangle on the circle. So here's an inscribed triangle. It's also true that each of the angles of the triangle, or whatever polygon you have inscribed in a circle, are inscribed angles. So this triangle ABC is an inscribed triangle. Angle BAC is an inscribed angle. The vertex of that angle is on the circle. Same with angle ABC and angle BCA. All of those angles lie on the circle. Each of the angles of an inscribed polygon are inscribed angles of the circle. Okay, and then also, besides the polygon being inscribed in the circle, it's also said that the circle is circumscribed about the triangle or whatever other kind of polygon. I could have a quadrilateral, PQRS, that's inscribed in a circle. So this would be an inscribed quadrilateral. All the vertices of the quadrilateral are on the circle. And then again, the circle is circumscribed about the quadrilateral. Or even something like a hexagon. 1, 2, 3, 4, 5, 6. All I'm doing is placing all 6 of the vertices. Since a hexagon has 6 sides, it would have 6 vertices. And then I'll label that hexagon, S, T, U, V, W, and X. All of the angles of the hexagon are inscribed angles of the circle. So with your inscribed polygons, that leads to the inscribed right triangle theorem, theorem 10.12. So the inscribed right triangle theorem states, if you have a right triangle, like I'm about to draw right now, there's my right angle, that's inscribed in a circle. So there's the third side. If this is a right triangle, then the side opposite the hypotenuse has to be a diameter of the circle. And then here's why. So if I label this right triangle ABC, C is your right angle, and AB, the side opposite the right angle, has to be a diameter. Angle C is an inscribed angle. It's 90 degrees. Here's the arc AB, or arc ADB, since it's a semicircle that it intercepts. It would be a semicircle because it would be twice the measure of the intercepted arc. Maybe to see a little bit easier, that arc ADB is a semicircle. You have to kind of pretend that segment or chord AB is not there. And this would be the inscribed angle. It would have to be twice that. This is 180 degrees. Again, that's a semicircle, which means chord AB, or the hypotenuse of the right triangle, has to be a diameter. And that means it passes through the center of the circle. So theorem 10.12, or the inscribed right triangle theorem, actually includes the conditional statement and the converse. I think this might be the first time we've ran across a theorem and its converse kind of rolled into one theorem itself, instead of being broken up into a theorem as one theorem, and then the converse would be a second theorem. Everything's kind of rolled into one. But like we were talking about, if a triangle is a right triangle and it's inscribed in a circle, then the hypotenuse has to be the diameter, and we explain why. But the converse of that is, if one side of a triangle, let's just say, without having to redraw this, you don't know that this triangle is a right triangle. If you know that one of the sides, in this case AB, is a diameter, then this has to be a right triangle, because the arc, that's the other angle, in this case C, intercepts, if this is a diameter, it would have to be 180 degrees, and then the intercepted arc would have to be half of that, 90 degrees. So this angle would be the right angle